In this session then, I would like to understand that if we treat a photon as a particle, then it must have a momentum. I would like to consider the implications that this has on matter as a wave. And I would like to introduce Schrödinger's equation and start to think about some of the things that come out of the Schrödinger equation and how this can help us in our understanding of the structure of the atom. In the last session then, I introduced the idea of the quantization of light energy and said that we can calculate the energy of a photon. And I introduced the photoelectric effect experiment and said that the energy of an incoming photon must be equal to or greater than this value we call the work function of a metal in order to eject an electron. And so if you shine light on the surface of a metal that has an energy greater than the work function, then you will eject an electron. If you shine light on a surface that doesn't have an energy that is equal to the work function of a metal, then an electron will not be ejected. And finally, even if you were to shine 3 photons onto the surface, however, each of those photons, if each of those photons does not have the energy that's equal to the work function, you still will not eject an electron from that surface. We said in the last session that photons can be described by their energy, their wavelength, or their frequency. We can also describe an electron that is released from the surface in the photoelectric effect by its kinetic energy, its velocity, or its wavelength. And I'd like to just introduce the idea of an electron volt here as being equal to 1.6 times 10 to the minus 19 joules. Let's do a calculation then that takes these concepts and works out whether or not we can expect to see an electron ejected from the surface of a zinc sample. So let's imagine that I have a zinc surface, and that zinc surface, or the atoms within that zinc, have a work function of 6.9 times 10 to the minus 19 joules. That means we've got to shine light onto that surface that has an energy greater than 6.9 times 10 to the minus 19 joules in order to observe the ejection of an electron. Let's imagine I've got 2 light sources and I shine those onto a zinc surface independently. I have a UV lamp that has a wavelength of 254 nanometers, and I have a red laser that has a wavelength of 700 nanometers. The question is, do either of these light sources have enough energy to emit a photon from the zinc sample? And we can work that out by calculating the energy per photon that is emitted from these light sources. So if I start with calculating the energy per photon for the red laser pointer, for example, I can use several equations that we've introduced in the last session. The first equation is the idea that the speed of light is equal to its wavelength multiplied by its frequency. And so I can also use the second equation here, that the energy of light, or the energy of a photon in this case, is equal to Planck's constant multiplied by the frequency. So we've been given here the wavelength of these light sources. So the first thing I need to do is convert the wavelength to a frequency. So I'm going to rearrange this equation up here to solve for the frequency. So the frequency therefore is equal to the speed of light divided by the wavelength. and I can do that calculation now. So I know the speed of light is equal to, I'm going to use a slightly less accurate value for the speed of light here, is 3 times 10 to the 8 meters per second. So that's 3 times 10 to the 8 meters per second. And I'm going to divide that by the wavelength here. The wavelength value I'm going to use should be in meters because I've got the speed of light in meters. So 700 nanometers is equal to 7 times 10 to the minus 7 meters. So 7 times 10 to the minus 7 meters. And that gives me a value of 4.6 times 10 to the 14 seconds, or hertz is the value for frequency. So 4.6 times 10 to the 14 hertz. So I've got frequency now, and I can now work out the energy per photon. And I'm going to do this by using the second equation that we've gone through here, E equals h nu, or E equals Planck's constant, multiplied by the frequency. So here the energy of my per photon of my red laser source is equal to Planck's constant, which is 6.626 times 10 to the minus 34. And I'm going to multiply that by the frequency that I've just converted. Let's put those in brackets. Multiply that then by the frequency, 4.6 times 10 to the 14 times 10 to the 14 hertz. And the value that I get is going to be in joules. It's an energy, and is equal to 3 times 10 to the minus 19 joules. So 3 times 10 to the minus 19 joules is a value in energy that is below the work function for this metal. And therefore, we would not predict, in this case, that an electron is ejected from that surface. Let's now calculate the value for the UV lamp. So again, let's first calculate the frequency now. So now the frequency is equal to, again, the speed of light divided by the wavelength. In that case, that's 3 times 10 to the 8, so speed of light being a constant, divided by the wavelength of my UV laser here, or my UV lamp, which is 254 nanometers, which is going to be 2.54 times 10 to the minus 7 meters. So 2.54 times 10 to the minus 7 meters, and I will get a value in hertz. And when you do that calculation, the number that you get is 1.18, so 1.2, we'll call it, times 10 to the 15. So 1.2 times 10 to the 15 hertz. Now I can calculate the energy per photon. That's my E equals Planck's constant multiplied by the frequency. So here I'm going to put Planck's constant in again. We'll put it in brackets. So that's 6.626 times 10 to the minus 34. And I'm going to multiply that value by the frequency, which I've just calculated as 1.2 times 10 to the 15. 1.2 times 10 to the 15. And when you do that calculation, the value that you get for the energy per photon for the UV laser source is 7.8 times 10 to the minus 19 joules. Now what you'll see now is that the energy of the photon for the UV laser lamp is greater than the work function for the metal, and we would predict that an electron is ejected from this surface. So we've seen then that the photoelectric effect was key in helping us to understand that light has particle-like properties, and we now think of light as both a wave and a massless particle. Now, if light is a particle, then each of those particles must have a momentum, and we can calculate the momentum of a photon by taking its energy, Planck's constant, multiplied by its frequency, divided by the speed of light. We also know that the speed of light is equal to the frequency multiplied by the wavelength, so we must be able to combine those two equations and calculate the momentum of a photon as being Planck's constant divided by its wavelength. Now the key conclusion here is that we are expressing momentum in terms of a wavelength, which is a strange thing because momentum is usually associated with mass and velocity. If we can have light as both a particle and a wave, why can't we have matter as a wave? We are comfortable with the idea of considering matter as a particle, but can we consider it as a wave? And the answer is yes. This work came as a result of Louis de Broglie's PhD thesis, and he proposed that if light waves exhibited the properties of particles, then matter particles should also exhibit the properties of waves, and that we could think about calculating the wavelength of these waves by the same equations. So here's our momentum. We can rearrange that equation to solve for wavelength. We know that momentum is equal to mass times velocity, so why can't we relate the wavelength of matter to its mass and velocity? So we're now expressing wavelength in terms of mass and velocity. We're thinking about the wavelength of matter now. And again, as I said, this all formed the work of de Broglie's PhD thesis. So let's think about that. Why don't we observe wave-like behavior of matter in our day-to-day activities? Let's think about a penalty kick taken by Mo Salah. We know the mass of the football, and we know the velocity at which Mo Salah kicks the ball. It's about 70 miles per hour or 31 meters per second, and we can calculate the wavelength of the football here. So I just take Planck's constant and divide it by the mass times the velocity of the football. And the answer we get out when we cancel through the units is that that football has a wavelength of 4.6 times 10 to the minus 34 meters. Now, that's far too small to observe. So we don't observe the wavelength of this matter because it's just far too small and we can ignore it. And if you like, you can work out which footballer's penalty kick has the longest wavelength. And when you do the mathematics, you see that it's Sadio Mane. Even still though, 5.2 times 10 to the minus 35 meters, it's too small to detect. It's irrelevant when we're talking about the matter, the size of matter that we deal with every day. Now let's think about the wavelength of a gaseous electron. An electron is much smaller and it moves at much more rapid speed. So an electron moves at 4 times 10 to the 6 meters per second, not an insignificant fraction of the speed of light there. When we calculate the wavelength of an electron now, the value comes out at 2 times 10 to the minus 10 meters. Now that's still a small number, it's equal to about 2 angstroms. But when we compare the wavelength of an electron to the diameter of an atom, suddenly it becomes important. The diameter of an atom is about 0.5 to 4 angstroms in size, and that's on the same scale as the wavelength of an electron. So because the wavelength of the electron is on the same scale as the object in which it resides, i.e. the atom, if the electron is a particle, then it's suddenly very important to talk about its wave-like behavior as well. So we think about the electron as both a wave and a particle. Now, is there any experimental evidence for the wave-like behavior of an electron? And indeed there is. In 1925, Davison and Germer diffracted electrons from a nickel crystal. Diffraction is usually a property that we associate with waves. So if you can diffract electrons, then they must have wave-like properties as well as particle-like properties. And G.P. Thompson also showed that when you pass electrons through a gold foil, you get a diffraction pattern. Once again, this is a wave-like property. So think about that. You've got J.J. Thomson and then his son, G.P. Thomson. In the early 1900s, you've got J.J. Thomson showing that an electron behaves as a particle from his experiments using cathode rays and his discovery of the electron. And in 1937, you've got G.P. Thomson, his son, showing diffracting electrons from a gold foil, showing that the electron behaves as a wave. And in fact, they both won the Nobel Prize. So one saying that the electron behaves as a particle, the other saying that the electron behaves as a wave. Well, the answer is they were both correct. The electron behaves as both a wave and a particle. What I'd like to do now ahead of the next session is just to briefly introduce the Schrodinger equation. So we know that matter, the electron, can behave as both a wave and a particle. What we need is a theory to explain this. So we spoke about in the first session the way that classical mechanics just does not explain this at all. And so the Schrodinger equation is an equation of motion for particles like electrons that account for their wave-like properties as well as their particle-like properties. And again, this is important because suddenly the wavelength of the electron is of the same size as the diameter of an atom. The simplest form of the Schrodinger equation is here. It can only be solved for the hydrogen atom or one electron systems. There is something called a Hamiltonian operator, and this details the total energy in terms of kinetic and potential energy of the system. There is a wave function, which tells us the probability of finding an electron in space. And there is this binding energy value. This tells us how tightly bound the electron is to the nucleus. Now, something that I will reiterate here, as I have done in lectures, is I am never going to ask you to solve or use this equation. We're only going to discuss it. I would like this course to develop a conceptual and qualitative understanding of quantum mechanics. This is not a mathematical course. Here's a slightly expanded form. You'll see that the Schrodinger equation for the hydrogen atom tells us some very important information. It tells us the distance from the nucleus at where we can find the electron. It tells us also some angular and orbital information about the position of the nucleus. So you can think of these as like coordinates on a map. The Schrodinger equation helps us to pinpoint the location of an electron as a function of distance and angle from the nucleus. The key conclusions that we make from the Schrodinger equation are that it tells us the probability of finding an electron in terms of its radial and orbital position, as well as the energy and distance of the electron from the nucleus. Some key conclusions are, and we'll be discussing this in the next session, that the binding energies of an electron are quantized, i.e. electrons sit in energy levels as we move away from the nucleus. We can think of those as orbitals.